All right, Physics 210 students, welcome. Let's dive right into Chapter 17 and the absolutely fascinating world of sound waves. We're going to be taking everything you learned about waves in Chapter 16 and applying it to the science of acoustics.
So here's what we've got on tap. We'll kick things off with the fundamentals. What even is a sound wave? Then we'll jump into how we measure sound. And this is cool. We'll look at the difference between physical intensity and how we perceive it as sound level. After that, we'll see what happens when waves smash into each other, creating interference and beats. And finally, we'll get to the really fun stuff, resonance and the Doppler effect.
Okay, first things first, what exactly are we talking about when we say sound wave? Let's get into the invisible mechanics behind everything you hear.
At its core, sound is a longitudinal wave. Now, what does that mean? It means that as the wave's energy moves forward, the particles of the medium, say the air, are vibrating back and forth in the same direction. The best way to picture it is with a slinky. If you push the end, you see a pulse of compression travel down its length. That's exactly what sound is, a moving series of high-pressure compressions and low-pressure expansions in the air. And this quote from your source material just nails it, right? It really gets to the core difference between sound waves and the transverse waves you might think of, like a ripple on a pond. With the transverse wave, the water moves up and down while the wave moves forward. But with sound, it's all about that push and pull, that compression and expansion in the direction of travel.
Okay, you're going to want to remember this number. For pretty much all the problems we'll be doing in Physics 210, this is your magic number for the speed of sound in air, 343 meters per second. Yeah, it can change a tiny bit with things like temperature, but for our calculations, this is the one. All right, so we know what sound is, but how do we measure it? This is where we bridge the gap between the raw physics of energy and the way our own ears and brains actually perceive loudness. Now, this is a super important distinction to get. We've got two different ways to talk about how loud a sound is: intensity and sound level. Intensity, measured in watts per square meter, is the pure raw physical power of the wave. But here's the thing, our ears don't work on a linear scale. That's where sound level, in decibels, comes in. It's a logarithmic scale that matches our perception. For example, a sound with 10 times the physical intensity only sounds about twice as loud to us. The decibel scale is built to reflect that human experience. And here's the kicker. Sound gets quiet, and it gets quiet fast. The intensity follows what's called an inverse square law. All that means is if you double your distance from a speaker, the intensity doesn't get cut in half. No, it drops to 1/4 of what it was. It fades out really quickly. So how do we get from that raw intensity number to the decibels we're all familiar with? Well, this formula is our key. It takes the massive range of intensities from the quietest whisper to a rocket launch and compresses it into a manageable scale. It does this by taking the logarithm of the ratio between the sound's intensity, I, and this reference intensity, I0, which is basically the faintest sound a person can hear. Okay, so what happens when two sound waves run into each other? Do they crash? Nope. In the world of waves, they actually pass right through one another. And the principle of superposition tells us that where they overlap, their amplitudes just add together. This simple idea leads to some really mind-blowing effects, like interference and beats. And when they overlap, you get one of two results. If the peaks of the two waves line up perfectly, they amp each other up, creating a much louder sound. We call that constructive interference. But if the peak of one wave lines up with the valley of another, they completely cancel each other out. You get quiet or even total silence. That's destructive interference. And it all comes down to one thing: the path difference, or how much farther one wave had to travel to get to you. You have totally heard this before. Ever listen to a band tune up and you hear that kind of wobble sound? That wah-wah-wah that gets faster as they get closer in tune? That's beats. It's what happens when two sound waves that have slightly different frequencies interfere with each other, creating a periodic rise and fall in loudness. And the math behind it is beautifully simple. The frequency of that wobble you hear is just the difference between the two frequencies of the sound sources. So if you have one guitar string vibrating at 440 Hz and another at 442 Hz, you're going to hear a beat frequency of 2 Hz, 2 wahs every second. All right, now we get to put all these pieces together and look at two huge real-world phenomena that you've definitely experienced: resonance, the magic behind why musical instruments work, and the Doppler effect, the reason a siren changes pitch as it screams past you. So resonance, what is it?
It's basically when you hit a system with just the right frequency and it goes wild, vibrating with a way bigger amplitude than it would otherwise. It's why a guitar has a hollow body, to resonate and make the strings loud. And this is the absolute core of what you're exploring in your standing sound waves in Air Columns lab. Let's take something like a flute or an organ pipe. At the open end, the air can go crazy, maximum vibration. We call that an antinode. But at the closed end, the air is stuck. It can't move. That's a node. And because of this physical setup, only very specific frequencies, these odd harmonics, can actually form a stable standing wave inside the pipe and make a clear, musical tone.
This is one of my favorite effects in all of physics, because you hear it literally all the time. You know that sound an ambulance makes? The pitch is high as it comes towards you, "Nui!" And then it drops low as it passes and moves away. "Nyu." That apparent change in frequency because of relative motion, that's the Doppler effect. So let's look at one version of the formula. If you, the detector, are moving away from a sound source, the sound waves get sort of stretched out from your perspective. That means you hear a lower frequency, a lower pitch. The big takeaway from the general formula is that the sign changes depending on your direction. Moving towards each other squishes the waves and gives a higher frequency. Moving away from each other stretches them and gives a lower one.
Okay, so as we wrap this up, I want to leave you with a real brain bender that pushes the Doppler effect to its absolute limit. Imagine a jet is flying past you, but it's moving at the exact speed of sound. What would you hear in the precise instant it's right in front of you? Think about it. It's been creating sound the whole time it was approaching, and all of that sound arrives at your ear at the exact same time. It's a pretty wild thought. Anyway, chew on that and we'll see you in the next explainer.